Now it's time to dig more deeply into this sort of problem. We're going to fill in a much more extensive table that will include not only the present state and the next state, but also the transitions necessary between those states, the conditions that will lead to those sorts of transitions, and what J and K inputs are necessary to cause those conditions. I'm going to scroll down to the bottom of this page here so that you can see this table is extremely important to us. So this table, I won't be constantly going back and forth to it because I have it printed out in front of me here, but you have to reference that table at almost every step of this process. And if you don't have that table in front of you, you could regenerate it, you could recreate that table, but it's much easier to just have it in front of you. When we get into these problems, there's so much going on with the problems that you don't want to have to constantly be thinking about, okay, if I go from 0 to 0, okay, I could do that with a reset, or I could do that with a hold, that's going to be a J, has to be 0, but I don't care what K is. You just want to be able to look it up on the table. So I just want to mention that I have that table in front of me here, and you'll want to have it in front of you to understand what's going on. Now we know that we want the modulus 4 down counter. That's the example that we just saw. So we already saw that if the present state is a 0, 0, the next state is going to be a 1, 1. 0, 1 is going to lead to a 0, 0. A 1, 0 is going to lead to a 0, 1. A 1, 1, that's going to lead to a 1, 0. Now the next thing we need to do is just simply break these up bit by bit. So I'll see that if I look at the most significant bit, and I'll just sort of dot it right there, that's the most significant bit, and I'm looking at the most significant bit right here, well that's a 0 to a 1. And if I look at the least significant bit, well the least significant bit is this one right here, and the least significant bit over here is this one right here, so that's also going to be a 0 to a 1. Looking at the most significant bit in the next value, that's a 0 to a 0, and a 1 to a 0 for the least significant bit. A 1 to a 0, and a 0 to a 1, a 1 to a 1, and a 1 to a 0. So you're just basically splitting it up into the two bits and considering the transitions for each bit. Then I need to look at that table that I mentioned. I see that a 0, 1, that's going to correspond to either a set or to a toggle. Again, set or toggle. And then a 0 to a 0, that's going to be a reset or a hold. And a 1 to a 0, that's going to be a reset or a toggle. 1 to 0 again is a reset or a toggle. A 0 to a 1, I've already seen that, that's a set or a toggle. And then a 1 to a 1, that's a set or hold. And a 1 to a 0, that's a reset or a toggle. Now I filled in all the conditions first, and then I'm going to go back and fill in the J and K inputs. But every time that I fill in one of these conditions, I could jump straight to the J and K inputs as well, because right in that same table, when I see set or toggle, I know that that corresponds to a 1x. So a set and a toggle, that's a 1x. Reset and a hold, reset or a hold, that's going to be a 0x. Reset or toggle, that's going to be an x1. Reset or toggle, again, x1. Set or toggle, that's a 1x. Set or hold, that's going to be an x0. Reset or toggle, that's going to be an x1. Now we're not completely done with the design process, but we've now done a great deal of the work necessary because what we've identified is these are the inputs. So the present state is the input to the next state decoder, and then over here these are the outputs. Because after all, the job of the next state decoder is to generate the J and K inputs, which will cause the system to transition into the correct next state when it receives the next clock pulse. Let's practice a couple more here. We have sort of an arbitrary pattern, 0, 2, 1, 3. We're doing the evens and we're doing the odds. So if I start in state 0, I know that I'm going to go to state 2. If I'm in state 1, the next state I go from 1 is to 3. So there's a 1, 1. 1, 0 is a 2. The next state after that is a 1. And if I'm in state 3, then I'm going to go back to state 0. So there I had to look at what pattern am I looking for to figure out what the next state is going to look like. The transitions, and I'll kind of do this a bit more quickly, but it's always good to go back and double check to make sure that you don't make any little mistakes. This is the sort of problem that it's very helpful to have a partner. So as you're doing it, you can check at each step with your partner to see if they're getting the, whoops, there's a mistake, to see if they're getting the, no, that's not a mistake, the previous one was a mistake. to see if they're getting the same answers that you're getting as well. So 0 goes to 1, 0 goes to 0, 0 goes to 1. Oh, yep, that's a mistake. 0 goes to 1, 1 goes to 1, 1 goes to 0, 0 goes to 1, 1 goes to 0, 1 goes to 0. Good. Then I can look those conditions up, and here I will show you how to do them sort of both at the same time. So if the transition is a 0 to a 1, I know that that's a set or a toggle, and I know immediately that that's a 1x. So it sort of saves a little time because you only have to do one lookup for each value. Also, I'll go ahead and do all of the 0 to 1s. So there's a set toggle, that's a 1x. Here's a 0 to 1, so that's a set toggle, and that's a 1x. So this just means that I don't have to go back to the table for each value. I go to the table once and then I fill in all of the cells that correspond to that. A 0 to 0, that's a reset or a hold. So there's a reset or a hold, and that corresponds to a 0x. And there are no other 0 to 0 transitions in this table. 1 to 1, that's a set or a hold. And a set or a hold can be done by an x0. And then are there any other 1 to 1s? There are not, but the three that remain are all 1 to 0. So 1 to 0 is a reset or a toggle. So reset or toggle, reset or toggle, and every reset or toggle is an x1. So it just makes the work a little bit easier if you can do it sort of value by value instead of cell by cell. Let's do one more, just so that you can get the pattern, because I think this is probably the step that is the hardest to get if you don't see enough examples. Here we're doing the 0, 3, 1, 2. I basically just try to choose a completely arbitrary order. So if I'm in state 0, I go to state 3. If I'm in state 1, I go to state 2. If I'm in state 2, I go to state 0. If I'm in state 3, I go to state 1. Break it up into the transitions. 0 to 1, 0 to 1. Let's see, this will be a 0 to 1 and a 1 to 0, 1 to 0, 0 to 0, 1 to 0, and 1 to 1. Again, I'm going to look each of these up in the table. 0 to 1, that's a set or a toggle. Again, you have to have that in front of you or else it's really very difficult to solve these problems. I have a few set toggles here. So there's one, another set toggle, and that's a 1x. Okay, and then the next one in order is a 1 to a 0. That's a reset toggle, and reset toggle can be done with an x1. 1 to 0 is a reset or a toggle, and that's done with an x1. Reset toggle x1. Let's see, the next one up is a 0 to 0. That's a reset or a hold. And a reset or a hold can be done with a 0x. And then the only cell that remains is a 1, 1. That's a set or a hold. And a set or a hold is done with an x0. So there's 3 examples sort of done in quick order where you can see how to fill in these tables of transitions, conditions, and inputs. Once we've got these done, now we're ready to do the next step, which is the actual design of the next state decoder.